Okay, last time at the end I introduced the concept of oxidation reduction and looked at the gradients of oxidation state of iron that we see in the Earth from metallic iron, oxidation state 0 in the core, to oxidation state 3+, ferric iron in surface regions. Now, as I was saying, rocks from deep in the crust or within the mantle have a dominance of iron 2+ over iron 3+. And so when they come to the surface and they sit around long enough in a wet environment, they weather, as we know, because in the surface environment, in equilibrium with oxygen in the air, Fe3+ is the stable state. So, for example, if we take an olivine, which is an Fe2+ mineral, this reacts, the iron in the olivine reacts with oxygen, and if you look at almost any igneous rock with iron-bearing minerals in it, it's rusted to make ferric oxide, Fe2O3, plus SiO2. So let's see, that's 4, 5, so that would be half an O2. So that's a way of writing down the oxidation of olivine, or the iron component of olivine, at the surface. This mineral is called hematite. All right, well, what actually happens, of course, is that although the net result looks like this, the olivine breaks down and it makes this iron oxide or iron hydroxide, both of which are stable at different conditions. What's really happening is that it's through the agency of water. Right? We know that weathering takes place in the presence of water. That's the catalyst for the whole oxidation process. So if you go to a desert, for example, you can pick up meteorites that have been lying there for hundreds of years and have not been altered at all because it's so dry. Even though they're not stable, they should oxidize, but they don't react fast enough. Or fortunately, they don't react fast enough, so we can still collect pristine samples. So why don't we write a more realistic reaction involving the agency of water? So Fe2SiO4 plus H2O goes to Fe2O3 plus SiO2. Let's just make that quartz again. And now we release 2H plus. And we've gone from Fe2 plus to Fe3 plus. And of course, going from Fe2 plus to Fe3 plus is an oxidation process, but equivalently to that, it is a loss of electrons. So we have 2 electrons. Like so. That's another way of writing a balanced reaction. Now we're using water as our medium. Okay, now we understand how to deal with H plus in terms of pH. But we can introduce another concept, which is PE. Minus the log of the electron concentration in solution is known as PE. Okay, so we have a kind of a little bit counterintuitive. If PE is very high, it means the electron concentration is low, and if this is low, it pulls the reaction this way. So if that's low, pulls the reaction this way. So the oxidized form is stable at high PE. Counterintuitive. All right. So what's happening is a low electron ion concentration, low electrons, means that this is low, which means that's stable, which means that this PE is a high number. And there are all sorts of equilibria. I've written another one down here, and that is the sulfate reduction. I better make sure I get this balanced. So sulfate goes to, there are various possibilities, but one is this one, H2S, 0 charge. And that needs, so we go from 2 minus to 0, so we need to have some hydrogens. And in fact, the balance looks like this: 8 electrons plus 10 hydrogens, because we have to use up those oxygens. Okay, so now you see that equilibrium, or that reaction as written, it's mass balance and it's also charge balance. So there's no net charge on this side and there's no net charge on that side. And I think it's right. So that's 2 and 10 electrons and 10 positive charges. Okay, and this is the well-known sulfate reduction reaction, or one of them. And we know that that bacteria in fact live on this reaction. They live on the free energy of this reaction, and they sit in very reducing environments. Sulfate comes in from seawater, and they convert, or they catalyze the conversion to the more stable form, which under reducing conditions is the H2S, and use the free energy as to sustain life. All right, so let's consider PE. And let's start with considering the stability of water. Now, we can write down the stability of water in equilibrium with oxygen, first of all. And the reaction is half O2 plus 2H plus 2 electrons equals H2O. Okay, so that's mass balanced and charge balanced, 0 charge both sides. And the log K for that reaction is 41.56 at 298. Okay, we're still messing around with log K's here. And so 41.56 equals log activity of H2O over activity of O2 to the half times H plus squared times E minus squared. So let's assume pure H2O and that's our standard state, activity is 1. We take the standard state of oxygen to be pure oxygen at 1 bar and 298, so we let this take place in pure oxygen. So the activity of oxygen will be 1, it being its standard state. So then 41.56 equals minus log let's keep it this way, 1 over H plus squared E minus squared. We can turn this upside down, change the sign, so it's minus 2, and we put the 2's outside, minus 2 log H plus minus 2 log E minus. Alright, turn it upside down, put the 2 outside, change the sign. And that, of course, is 2pH. And that is 2pe. So we divide 2 and we get 20.78 equals pH plus PE. Okay, so what? Well, what we can do now is we can draw another diagram. Another kind of activity diagram. This one I'm going to call a pH-PE diagram. Alright, so I'm going to plot this on a line. So obviously PE is 20.78 minus pH. Okay, that would be the equilibrium of water with pure oxygen, defined by that line. PE equals 20.78 minus pH. So actually, I'll just put it over here so as you can see it at the same time. So we can plot this diagram, PE against pH. And let's put 20 there and 0 there. pH would be 0. And let's say 14 would be there. And that upper line looks more or less like so. I kind of missed it, but it should come down to, so it should be a bit steeper than that. Still not doing very well, but anyway, good enough. Slope should be -1, of course. So this is the slope, this is this line, And of course, water is stable on the side in which the electron concentration is high, right? So we pump up this and we drive the reaction this way. Okay? So water is going to be stable on the side in which, by Le Chatelier's principle, we drive the reaction to the right by raising the electron ion concentration, which means lowering PE. So H2O is here at low PE and oxygen is there. And that's the upper stability of water at 298. And 1 atmosphere. So what about the lower stability? Well, some of you in school may have done the hydrogen electrode. And that is where you put a platinum electrode in water and you pass pure hydrogen over it. Sounds like the sort of thing they find a bit dangerous these days. I remember we did it when I was in school. Nobody worried about it. We used to play with liquid mercury as well, so that's why I'm bald and a bit crazy. Anyway. The opposite of oxidation is reduction, and to reduce things, we stick them in hydrogen. Hydrogen is one of the most, probably the most reducing substance on Earth. So we consider then the hydrogen electrode, where we have 1 atmosphere of hydrogen pressure. And that's simple. H2 equals 2H plus 2E minus. Okay, charge balance and mass balanced. And at 1 atmosphere of hydrogen, we're going to be much more reducing with that down here. And the log K of that reaction is given a value 0 by convention. The reason for that is, as I explained before, all of these free energies and log Ks that we're dealing with, all are relative to something. There are no absolute values. Now, normally we give tabulate free energy in terms of values relative to the constituent elements. But for solution chemistry, they have to have a reference point, and this is the reference point. It's the hydrogen electrode. So now, 0 is the log of H plus, well, we can divide by 2, it doesn't matter, it's 0 over 2 is 0, over times E minus over H2, sorry, activity of hydrogen, activity of H2 to the half. We have 1 bar of hydrogen, so it's in its standard state, the activity is 1. So that disappears, so 0 is equal to minus pH minus PE. Or PE is 0 minus pH. Okay? So PE is 0 minus pH. Off in that direction. And the 2 lines are parallel. Okay, this is the upper line, and this is the lower line. And same argument, if you pump up the electron concentration, you're going to make hydrogen. Okay, you pump it up, you'll make hydrogen. Now, high electron concentration is low Pe. So hydrogen is down here. And H2O is there. And this is the entire field of aqueous geochemistry. Aqueous. All right, so let's look at that sulfate reduction reaction again, and just plot it on this. Plot the sulfate reduction reaction on this diagram. Actually, I'm going to plot two reactions involving sulfate. So, and then assuming that I can get PowerPoint to work on this thing, I'll show you what the full diagram looks like. Anyway. So here's a SO4 2 minus. And this time I'm going to reduce it to HS minus. Okay? So plus 9H plus. Well, no, just see if I can balance it. So that's HS minus plus H2O. Alright. So instead of reading it out, see if I could do it. So 9H plus. So we'll end up, we need 4, that will give us 4 waters. There's 1 sulfur. So 4 H2O, the oxygens are balanced. And we've got 1 too many electrons. So we need E minus. Sorry, got it wrong. I forgot about the H plus. Alright, so we got 1 minus on this side. We've got 7 plus and 2 minus on that side is 7 plus. So 7 plus and 1 minus, we need 8 electrons. Okay, and the log K for that reaction, according to my numbers here, is 33.66. Which, if I can remind you, is minus delta G0 over 2.303 RT. And the T is 298. Okay, so 33.66. Is equal to log HS minus over SO4 2 minus activity of water to the 4th, H plus to the 9th, and E minus to the 8th. Now what I'm going to do here is I'm going to consider the conditions under which these are equal in concentration. Alright? So we set the activity of water equal 1. Being more or less in its standard state. And that will tell us that 33.66 is equal to log, and I'll just separate these out from that. HS minus over SO4 2 minus and these are underneath, so negative, minus 9 log H plus minus 8 log E minus. And that's 8 PE, and that's 9 pH. So what we'll do is we'll set HS minus over SO4 2 minus equals 1. Log of 1 is of course 0. And we get that 8 PE will equal 33.66. That's plus 9 pH, put it on the other side, minus 9 pH. Or PE is equal to 33.66 over 8, which is 33.66 divided 8, 4.2. What have I got here? 4.2, yeah, okay. 4.2 minus 9/8 pH. So we can put it on our diagram. Not sure this is in view. Here's a PE-pH diagram. That's 20. That's 0. And that's H2O. And this one is 4.2 minus 9/8, so slightly steeper slope. Like so. Maybe I should make it red, might look a little bit more interesting. It's like that. Again, we ask the question, which side is which? Okay, so if we pump up the electron ion concentration, we're going to drive the reaction towards this, which is bisulfide. So this is stable when the electron concentration is high, which is when PE is low. So HS minus is there, and SO4 2 minus is there. Okay. Well, there's another form of this sulfide ion, and that is the H2O. H2S 0. So we can run another reaction, which is H2S 0 goes to HS minus plus H plus. Okay, so if the hydrogen ion concentration gets really high, we make this one. push it that way and make this one instead of HS minus. So where will that be? According to my calculations, log K is minus 6.99. So minus 6.99 then is equal to log HS minus over H2S plus log of H plus. Just separated out from log K. So that's minus pH and that says that for equal amounts where H2S and H2S and HS minus are both an equal amount, so that log is 0. Minus pH equals minus 6.99, so pH equals 6.99. And of course, it's independent of PE because there are no electrons lost or gained in this reaction. Okay? So the oxidation state of sulfur is the same in bisulfide as in H2S. So there'll be a vertical line. That vertical line will correspond. There's a lot of Le Chatelier's principle here, I'm afraid. That vertical line corresponds to equal amounts. So that's equal amounts of sulfide, sulfate and bisulfide. And that line corresponds to equal HS minus and H2S. So the same, the H2S is going to be stable. If we pump up the hydrogen ion concentration, we drive the reaction that way and we make H2S. So H2S is stable if hydrogen ion concentration is high. Hydrogen ion concentration high corresponds to low pH. So actually, this should be H2S in here. And HS minus will be there. So HS minus is only stable at high pH, and the high pH is where this is low, so this is pulling the reaction to the right. Okay, I have a complete diagram on a PowerPoint, which I'm going to hopefully will manage to fold into this lecture in a moment. All right, final point. Let's take an example where, okay, we've done these reactions in solution. So everything here is in solution. But of course, we're interested in how much iron or how much sulfur would there be in solution if we were saturated in sulfide. As you know, in reducing sediments, you get pyrite, iron sulfide. So how much sulfur would you have in the solution at the point at which pyrite precipitates? Or, let's say in the case of iron, which is the one I've written down here to go over, in the case of iron, how much iron are we going to have in solution when we're saturated in iron oxide or any iron silicate? Okay, so let's just do that calculation. So we'll look at the dissolution of ion of Fe2O3. Now, actually, I have a slight extension of this problem in the practical for this week. So this gives us, I hope, a good introduction to it. So the thing is, something which we will find out if and when you do the calculation, is that Fe3 plus oxidized ion is very insoluble in water. Okay? Fe2 plus, on the other hand, is soluble. So when we undergo oxidation, when we oxidize iron 2 plus in solution, we tend to, instead of making iron 3 plus in solution, we make a precipitate. We precipitate it. So Fe3 plus is very insoluble. Fe2 plus is soluble. A useful thing to remember. So, as an example, I used to do it when I was in Bristol 20 odd years ago. I used to run the field trip to Cornwall, and at that time, they were just closing down the tin mines. And the tin mines have a lot of sulfides in them, and as they close them down, they fill with water. And then the water comes out of the old adits, spills into the drainage system, into the rivers, and eventually down into the sea. And what happened, it was very interesting. It was around the time we were down there, one of them old mines flooded. Now the water in the mines is very acid, and it's very reducing. Okay? And so it was very, very full of Fe2 plus. From all the sulfides and the iron-bearing minerals that are in the granites there. And so this stuff came pouring out of the adits, and it's acid, reduced, full of iron 2 plus, and as soon as it hit the air, bingo, iron Fe3 plus was produced, and it produced red iron oxide. And the rivers were just full of this iron oxide, and it all flowed into the Falmouth Harbour, Carrick Roads. And it's just a nightmare. The sea was brown, reddy brown, horrible. Anyway, that's because the Fe3 plus is very insoluble. As soon as it oxidized in contact with the air, it precipitated. So let's look at that reaction. How convenient. Right, so I've written it this way around. Hematite, iron oxide, plus 2 electrons, plus 6 hydrogens, is equal to 2 Fe2 plus 3 H2O. Okay, so here we have iron 2 plus in solution. And that should hopefully be charge balance is 4. 6 minus 2 is 4 on that side. And log K for that reaction, well, delta G0 is minus 126,480 joules at 298. So log K is equal to plus 126,480 over 2.303 times 8.314 for R times 298, and that equals 22.16. So 22.16 is the log of Fe2 plus squared times the activity of H2O cubed over the activity of Fe2O3 times electron activity squared times hydrogen ion activity to the sixth. So let's say pure water, and the activity of Fe2O3 was saturated in hematite. So 22.16 is equal to 2 log Fe2 plus minus 2 log E minus minus 6 log H plus. So now we let's just divide by 2. Is that a good idea? I think so. So we do that. So it's 11.08 equals log Fe2 plus plus Pe plus 3 pH. Okay, divided by 2. So now we've got 3 unknowns, kind of difficult to plot on our PE-pH diagram. But there is a convention. Of course, there's always a convention, isn't there? So the convention is that when we are plotting these diagrams, if we have a solution species in equilibrium with a solid, we set the activity of the solid to 1, which we've done, and we set the activity of the solution species to 10 to the minus 6. Okay? So we set, by convention, Fe2 plus equals 10 to the minus 6. So what does that mean? It means that if we get a value that's lower than 10 to the minus 6, we treat the mineral as insoluble. If we get a value which is higher than 10 to the minus 6, then we treat it as if it were in solution. All right, it's just a way of drawing the diagram. Okay, so let's go through that exercise. So 11.08 is equal to log of 10 to the minus 6 is minus 6 plus Pe plus 3 pH, or 17.08 minus 3 pH equals Pe. So that will give us a line so PE-pH diagram. I think I've rubbed it out. Here's 0, there's 20, so it's 17 That's a stability limit of water. At 17, it's got a very steep, much steeper slope, 3. Okay, so this is our slope for this reaction. PE 17.08 minus 3 pH. May have drawn it a little bit too steeply, but never mind. And so, which side? So on the high side, if we increase the E minus concentration, we drive it this way. Increasing E minus is lowering PE. So Fe2 plus is on that side, and Fe2O3 on this side. Okay, so if the conditions are more oxidized or less acid than that line, then we treat Fe2O3 as if it's completely insoluble. If they're more acid or more reducing than that line, then we treat it as Fe2 plus in solution. We can change that. Sometimes people use 10 to the minus 3 instead of 10 to the minus 6. Obviously, it's simply a way of representing the equilibrium on a diagram. Final thing I wanted to say is that these PE-pH diagrams can be represented a slightly different way as EH-pH diagrams. And I think that Ros Rickaby treats them that way. So just to tell you the relationship, there's a very simple linear relationship between PE and EH, which is electropotential. EH is the electropotential, given the symbol EH. And that's equal to, well, it's got Faraday's constant and temperature in it, so it's, make sure I get it right, otherwise I'll, and of course, lost it. Okay, EH is 2.303 RT divided by Faraday's constant times PE. This is 96,500 coulombs per mole. And these have the usual meaning. So that's equal to 0.059 PE. And when you plot the diagram, it looks just the same, of course. Except EH goes up to just over 1 instead of PE, which is just over 20. So the diagram, the topology of the diagram is exactly the same. Nothing to get too exercised about.